Grains in a breccia are angular, indicating that the material was deposited closer to its source area. Conglomerate is made of rounded grains, implying a significant amount of transport before deposition. Examine these sketches of sediment particles. Which particle, A, B, or C, has traveled farthest from its source? Explain your reasoning. 7.3 Chemical sedimentary rocks. Explain the processes involved in the formation of chemical sedimentary rocks and list several examples. Key terms: biochemical limestone, dolostone, chert, evaporite, salt flat. Chemical sedimentary rocks are formed when ions dissolved in solution link together to form mineral crystals. Sometimes this happens inorganically, and other times living organisms biochemically extract the ions to precipitate mineral matter as bone or shell. Limestone is the most common chemical sedimentary rock. It forms mainly in shallow, warm ocean settings. Limestone is dominated by calcium carbonate. This is the material from which corals construct reefs. Coquina and chalk are also examples of biochemical limestone. Travertine and oolitic limestone are examples of inorganic limestone. Dolostone is a chemical sedimentary rock that is dominated by the mineral dolomite. Like calcite, dolomite is a carbonate mineral, but about half of its calcium ions have been replaced by magnesium ions. Chert is the general term for rocks made of microcrystalline silica. If the chert is red, it is called jasper. Black chert is flint. Agate is multicolored. When silica replaces plant matter to make petrified wood, often a variety of colors are present. Evaporite deposits form when minerals precipitate from an ever more concentrated solution of dissolved ions. This is how the vast salt flats of the American West formed. Digging into these deposits reveals rock salt, rock gypsum, and the potassium salt sylvite. Does this rock salt more likely have a biochemical or an inorganic origin? 7.4 Coal, an organic sedimentary rock. Outline the successive stages in the formation of coal. Key term: coal. Coal forms from large amounts of plant matter buried in low-oxygen depositional environments such as swamps and bogs. Through compression, the peat formed becomes compressed into a low-grade form of coal called lignite. Lignite can be compressed further, driving out volatile components and concentrating carbon to make higher-grade bituminous coal. Metamorphism accompanying mountain building can take this concentration process even further, producing the highest grade coal, anthracite. Considering that it comes from plants, what is the ultimate source of the energy in coal? 7.5 Turning sediment into sedimentary rock, diagenesis and lithification. Describe the processes that convert sediment into sedimentary rock and other changes associated with burial. Key terms: diagenesis, lithification. Compaction, cementation. When sediments are buried to relatively shallow depths, changes in temperature and pressure trigger a variety of processes called diagenesis, a collective term for all the chemical, physical, and biological changes that occur after sediments are deposited and during and after lithification. The transformation of sediment into sedimentary rock is called lithification. The two main processes contributing to lithification are compaction and cementation. 7.6 Classification of sedimentary rocks. Summarize the criteria used to classify sedimentary rocks. Key terms: clastic, non-clastic. Sedimentary rocks are classified primarily based on whether they are detrital, chemical, or organic. Detrital rocks are subdivided by grain size, while among the chemical rocks, mineral composition is the key distinguishing characteristic. An additional characteristic is whether the rocks exhibit a clastic or non-clastic texture. Crystalline texture is common to non-clastic sedimentary rocks and igneous rocks and is particularly apparent under magnification. However, the minerals involved are totally different and allow the two types of rock to be distinguished. Would a limestone made of shell fragments be detrital or chemical? Would its texture be clastic or crystalline? 7.7 Sedimentary rocks represent past environments. Distinguish among three broad categories of sedimentary environments and provide an example of each. List several sedimentary structures and explain why these features are useful to geologists. Key terms: environment of deposition: facies, strata bedding, plain cross-bedding, graded bed, ripple mark, mud, crack, fossil. Different combinations of tectonic, climatic, and biological conditions result in different types of sediment accumulating. The principle of uniformity suggests that the sedimentary record can be interpreted in light of modern depositional environments. Continental, marine, and transitional environments all have distinctive characteristics that allow geologists to identify sedimentary rocks formed in those environments. Sedimentary facies are lateral equivalents that represent different depositional conditions operating in adjacent areas at the same time. For instance, a beach today may be depositing sand, while a kilometer or two offshore only mud is being deposited, and further beyond that, carbonate minerals may be precipitating. All are the same age but represent neighboring areas governed by different conditions. Sedimentary structures are patterns that form in sedimentary rock at the time of deposition, before the sediments become lithified. They can provide powerful clues to the conditions under which the sediment accumulated. Beds are sheets of sediment deposited in a more or less continuous layer. Sometimes crossbeds are preserved within bedding, allowing geologists to deduce the direction of the depositional current. Ripple marks, small waves created by wind or water on the surface of a sediment layer, also provide useful clues. Graded beds indicate depositional currents that quickly lost their energy. Larger grains settled out first, and the smallest grains settled out last. Mud cracks form when mud contracts upon drying out, and they indicate that the sediment was exposed to air. Fossils serve as useful tools that allow geologists to date and interpret past environmental conditions. The accompanying photo shows Los Osos Creek entering California's Morro Bay. Sediment transported by the creek has been deposited as a delta. Which broad category of sedimentary environment is represented in the scene? 7.8 Resources from sedimentary rocks. Distinguish between the two broad groups of non-metallic mineral resources. Discuss the three important fossil fuels associated with sedimentary rocks. Key terms: non-metallic mineral resource, building material, industrial mineral, fossil fuel source, rock, oil trap, reservoir rock, cap rock, hydraulic fracturing. Earth materials that are not used as fuels or processed for the metals they contain are referred to as non-metallic resources. Many are sediments or sedimentary rocks. The two broad groups of non-metallic resources are building materials and industrial minerals. Limestone, perhaps the most versatile and widely used rock of all, is found in both groups. Coal, oil, and natural gas are all fossil fuels. In each, the energy of ancient sunlight, captured by photosynthesis, is stored in the hydrocarbons that made up plants or other living things and that were then buried by sediments. Coal is formed from compressed plant fragments, originally deposited in ancient swamps. Burning it supplies about 18% of U.S. energy use. Coal mining can be risky and environmentally damaging, and burning coal generates several kinds of pollution. Oil and natural gas are formed from the heated remains of marine plankton. Together, they account for about 60% of U.S. energy use. Both oil and natural gas leave their source rock and migrate to an oil trap made up of other, more porous rocks, called reservoir rock, covered by a suitable impermeable cap rock. Hydraulic fracturing is a method of opening up pore space in otherwise impermeable rocks, permitting natural gas to flow out into wells. As you can see here, the Sinclair Oil Company's logo speaks directly to the fossil nature of the fuel it sells. However, is it likely that any dinosaur carbon has ended up in Sinclair's oil? Explain. 7.9 The carbon cycle and sedimentary rocks. Relate weathering processes and sedimentary rocks to the carbon cycle. Key term: carbon cycle. Carbon is a vital component of the atmosphere, biosphere, geosphere, and hydrosphere. The same atom of carbon that is currently part of your nose may have entered your body in a piece of bread. Prior to that, it may once have been part of a plant, and before that it may have been a carbon dioxide molecule in the atmosphere. How did it get to the atmosphere? Perhaps it escaped into the air after originally being dissolved in the ocean, and perhaps it got to the ocean by being weathered from limestone and then washed down a stream. While individual details vary, the key point is that carbon is a reactive element that is equally at home in rocks, water, the air, and living tissue. Give it some thought. 1. Develop a geologic life history of a sedimentary rock. Begin with a mass of igneous bedrock in a mountain area and end with your sedimentary rock being collected by a future geology student. Be as complete as possible. 2. How is the use of the term clay in relation to minerals different from the use of the term in Figure 7.3? How are these two uses of the term related? 3. This detrital rock consists of angular grains and is rich in potassium feldspar and quartz. What do the angular grains indicate about the distance the sediment was transported? The source of the sediment in this rock was an igneous mass. Name the likely rock type. Did the sediment in this sample undergo a great deal of chemical weathering? Explain. 4. If you hiked to a mountain peak and found limestone at the top, what would that indicate about the likely geologic history of the rock atop the mountain? 5. Why is it not necessary to indicate the texture of detrital rocks on the identification chart for sedimentary rocks? 6. During a hike in Utah's Zion National Park, you pick up a sedimentary rock sample. When you examine the sample with your hand lens, you see that the rock consists mainly of rounded glassy particles that appear to be quartz. To be sure, you conduct two basic tests. When you check for hardness, the rock easily scratches glass, which is what quartz would do. However, when you place a drop of acid on the sample, it fizzes. Explain how a rock that appears to be rich in quartz could effervesce with acid. 7. Examine the accompanying sketch, which shows 3 sediment layers on the ocean floor. What term is applied to such layers? What process was responsible for creating these layers? Are these layers more likely part of an offshore lagoon or a deep-sea fan? 8. This image shows the surface of a sand dune. What term is applied to the wave-like ridges on the surface? Be as specific as possible. Is the prevailing wind direction most likely from the left or from the right? Explain. 9. This rock sample consists of intergrown crystals. How would you determine whether the rock is sedimentary or igneous? If it is sedimentary, what term describes its texture? 10. This chapter includes a discussion of industrial minerals. Are these substances actually minerals? That is, do they meet the definition of mineral outlined in Chapter 3? Explain. 11. Follow the history of a single carbon atom as it moves from one part of the Earth system to another. Using any order you choose, include as many of the following sites as possible: a cave, a river, a dinosaur, a coal-fired power plant, a volcanic eruption, a swamp, a can of beer, and a coral reef. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 8: Metamorphism and Metamorphic Rocks. Metamorphic rocks exposed on an island in Georgian Bay, Ontario, Canada. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 8.1 Compare and contrast the environments that produce metamorphic, sedimentary, and igneous rocks. 8.2 List and distinguish among the four agents that drive metamorphism. 8.3 Explain how foliated and non-foliated textures develop. 8.4 List and describe the most common metamorphic rocks. 8.5 Write a description for each of these metamorphic environments: contact metamorphism, hydrothermal metamorphism, subduction zone metamorphism, and regional metamorphism. 8.6 Explain how index minerals are used to establish the metamorphic grade of a rock body. The folded and metamorphosed rocks shown in the chapter opening photo were once flat-lying sedimentary strata. Compressional forces of unimaginable magnitude, combined with temperatures hundreds of degrees above surface conditions, prevailed for perhaps thousands or millions of years to produce the deformation displayed by these rocks. Under such extreme conditions, solid rock responds by folding, fracturing, and often flowing. This chapter looks at the tectonic forces that forge metamorphic rocks and how these rocks change in appearance, mineralogy, and sometimes overall chemical composition. 8.1 What is metamorphism? Compare and contrast the environments that produce metamorphic, sedimentary, and igneous rocks. Unlike some igneous and sedimentary processes that occur in surface or near-surface environments, metamorphism most often occurs deep within Earth, beyond our direct observation. Notwithstanding this significant obstacle, geologists have developed techniques that allow them to learn about the conditions under which metamorphic rocks form. In turn, the study of metamorphic rocks provides important insights into how tectonic processes operate to alter the structure and composition of Earth's crust. Recall from the discussion of the rock cycle in Chapter 1 that metamorphism is the transformation of one rock type into another rock type. Metamorphic rocks are produced from pre-existing sedimentary and igneous rocks, as well as from other metamorphic rocks. Thus, every metamorphic rock has a parent rock, the rock from which it was formed. Metamorphism, which means to change form, is a process that transforms the mineralogy, texture, and sometimes chemical composition of the parent rock. The mineralogy changes because the rock is subjected to new conditions, usually elevated temperatures and pressures, which are significantly different from those in which it initially formed. For example, clay minerals, which are the most common minerals in sedimentary rocks, are stable only at Earth's surface. When clay minerals are buried to a depth where temperatures exceed 200 C, they are transformed into the minerals chlorite and/or muscovite mica. Under more extreme conditions, chlorite becomes biotite mica. Metamorphism also alters a rock's texture, producing larger crystals and sometimes a distinct layered or banded appearance. The degree to which a parent rock changes during metamorphism is called its metamorphic grade, and it varies from low grade to high grade. For example, in low-grade metamorphic environments, the common sedimentary rock shale becomes the more compact metamorphic rock slate. During this transformation, the clay minerals in shale are transformed into tiny chlorite and muscovite mica flakes. Hand samples of slate and shale are sometimes difficult to distinguish from one another, illustrating that the transition from sedimentary to metamorphic rock is often gradual and the change subtle. Figure 8.1 Metamorphic grade. Here low-grade metamorphism is illustrated by the transformation of the common sedimentary rock shale to the more compact metamorphic rock slate. B. High-grade metamorphic environments obliterate the existing texture and often change the mineralogy of the parent rock. High-grade metamorphism occurs at temperatures that approach those at which rocks melt. Figure 8.1 Full alternative text description. In environments where temperatures and pressures are more extreme, metamorphism causes a transformation so complete that the identity of the parent rock cannot be easily determined. In high-grade metamorphism, such features as bedding planes, fossils, and vesicles that existed in the parent rock are obliterated. Further, when rocks deep in the crust are subjected to compressional stress, the entire mass may be deformed, usually by folding. Figure 8.2 illustrates the relationships among metamorphic, sedimentary, and igneous environments. Metamorphism occurs over a range of temperatures that lie between those experienced during the formation of sedimentary rocks and temperatures approaching those at which rocks begin to melt. However, during metamorphism, the rock remains essentially solid. If significant melting occurs, the rock has entered the realm of igneous activity, as discussed in Chapter 4. Metamorphism occurs over a range of temperatures that lie between those experienced in sedimentary environments and temperatures that approach those at which rocks melt. Pressure, which includes confining pressure and differential stress, also plays a major role in metamorphism. Figure 8.2 Metamorphic versus sedimentary and igneous environments. Figure 8.2 Full alternative text description. Pressure also plays an important role in metamorphism. Although confining pressure acts to compact sediment to form sedimentary rocks, the pressures involved in metamorphism are even greater, sufficient to convert mineral matter into denser forms having more compact crystalline structures. Thus, metamorphism involves the formation of new minerals from pre-existing ones. Concept checks 8.1. 1. Metamorphism means to change form. Describe how a rock may change during metamorphism. 2. What is meant by the statement every metamorphic rock has a parent rock? 3. Define metamorphic grade. 8.2 What drives metamorphism? List and distinguish among the 4 agents that drive metamorphism. The agents of metamorphism include heat, pressure, differential stress, and chemically active fluids. During metamorphism, rocks may be subjected to all 4 metamorphic agents simultaneously. However, the degree of metamorphism and the contribution of each agent vary greatly from one environment to another. Heat as a metamorphic agent. The most important factor driving metamorphism is heat because it provides the energy needed to produce the chemical reactions that result in the recrystallization of existing minerals. Recall from the discussion of igneous rocks in Chapter 4 that an increase in temperature causes the atoms within a mineral to vibrate more rapidly. Even in a crystalline solid, where atoms are strongly bonded, this elevated level of activity allows individual atoms to migrate more freely between sites in the crystalline structure. Changes caused by heat. The formation of new or enlarged mineral grains at the expense of original grains is called recrystallization. During this process, the mineralogy of the rock may or may not change, but grains tend to become larger. For example, when quartz sandstone is metamorphosed to form quartzite, the mineralogy does not change. Both rocks consist of quartz, but the process results in fewer and larger quartz grains. By contrast, when shale is metamorphosed to slate, the clay minerals are recrystallized and become new minerals, usually chlorite and muscovite. Although the mineralogy changes in the transition from shale to slate, the overall chemical composition remains essentially unchanged. Instead, the existing atoms are rearranged into new crystalline structures that are more stable in the new environment. What is the source of heat? There are 2 primary ways in which a rock may become hotter. First, it may become more deeply buried. Earth's temperature rises with depth. Second, a magma body may be placed nearby, heating the surrounding rocks. Earth's interior is extremely hot, mainly because of heat released from the repeated collision of asteroid-sized bodies during the formation of our planet, as well as from energy being continually released by the decay of radioactive elements. The rate of increase in temperature with depth is known as the geothermal gradient. In the upper crust, this increase in temperature averages about 25 C per kilometer. Thus, rocks that formed at Earth's surface experience a gradual increase in temperature if they are transported to greater depths. As described earlier, clay minerals tend to become unstable when buried to a depth of about 8 kilometers, where temperatures are about 200 C. The clay minerals begin to recrystallize into new minerals, such as chlorite and muscovite, both of which are stable in this new environment. However, many silicate minerals, particularly those found in crystalline igneous rocks, such as quartz and feldspar, remain stable at these temperatures. Thus, metamorphic changes in quartz and feldspar generally occur at higher temperatures. Smart Figure 8.3 Sources of heat for metamorphism. The two main sources of heat for metamorphism are the increasing temperature that occurs as we travel deeper into Earth's interior and heat released to the surrounding rocks when a magma body cools. Smart Figure 8.3 Full alternative text description. Watch tutorial, Metamorphic environments. Figure 8.3 provides several examples of conditions in which heat drives metamorphism. Environments where rocks may be carried to great depths and heated include convergent plate boundaries, where slabs of sediment-laden oceanic crust are being subducted. Rocks may also become deeply buried in large basins, where gradual subsidence results in thick accumulations of sediment. These basins, exemplified by the Gulf of Mexico, are known to develop low-grade metamorphic conditions near the base of the pile. In addition, continental collisions, which result in mountain building, cause some rocks to be uplifted while others are thrust downward, where elevated temperatures and pressures trigger metamorphism. Heat may also be transported from the mantle into the shallowest layers of the crust. Rising mantle plumes, upwelling at mid-ocean ridges, and magma generated by partial melting of mantle rock at subduction zones are three such examples. When magma intrudes rocks at shallow depths, the magma cools and releases heat, which bakes and transforms the surrounding host rock. Did you know? The temperature of Earth's crust increases with depth, an idea that can be expressed as the deeper one goes, the hotter it gets. This causes considerable problems for underground mining efforts. In the Western Deep Levels mine in South Africa, which is 2.5 miles deep, the temperature of the rock is hot enough to scorch human skin. Here, the miners work in groups of two, one to mine the rock, and the other to operate the fan that keeps them cool. Confining pressure. Pressure, like temperature, increases with depth because the thickness of the overlying rock increases. Buried rocks are subjected to confining pressure, which is analogous to water pressure, in which the forces are applied equally in all directions. Imagine scuba divers, the deeper they dive, the greater the confining pressure. Smart Figure 8.4 Confining pressure and differential stress. Smart Figure 8.4 Full alternative text description. Confining pressure causes the spaces between mineral grains to close, producing more compact rocks that have greater densities. If the pressure becomes extreme enough, it can cause the atoms in a mineral to pack more closely together to produce a new, denser mineral. Recall from Chapter 3 that the transformation of one mineral to another is called a phase change. Confining pressure does not, however, fold or fracture rocks. Watch tutorial, Confining pressure and differential stress. Differential stress. In addition to confining pressure, rocks may be subjected to directed pressure. This occurs, for example, at convergent plate boundaries where slabs of lithosphere collide. Here the forces that deform rock are different in different directions and are referred to as differential stress. Unlike confining pressure, which squeezes rock equally in all directions, differential stresses are greater in one direction than in others. Differential stress that squeezes a rock mass as if it were placed in a vise is termed compressional stress, as shown in Figure 8. For B, rocks subjected to compressional stress are shortened in the direction of greatest stress and elongated, or lengthened, in the direction perpendicular to that stress. Along convergent plate boundaries, the greatest differential stress is directed horizontally in the direction of plate motion. Consequently, in these settings, the crust is greatly shortened and thickened, resulting in mountainous topography. In high-temperature, high-pressure environments, rocks are ductile, which allows their mineral grains to flatten when subjected to differential stress. The metaconglomerate, also called the stretched pebble conglomerate, shown in Figure 8. 5, illustrates this tendency. The parent rock, a conglomerate, consisted of nearly spherical pebbles that have been flattened into elongated structures by differential stress. On a larger scale, rocks that are ductile deform by flowing rather than breaking or fracturing. As a result, deeply buried rocks subjected to extremely high temperature and pressure will develop intricate folds when deformed by differential stress. This metaconglomerate is made of once nearly spherical pebbles that have been heated and flattened into elongated structures by differential stress. Figure 8.5 metaconglomerate, also called stretched pebble conglomerate. Figure 8.6 deformed and folded gneiss, Anza-Borrego Desert State Park, California. By contrast, in near-surface environments where temperatures and pressure are comparatively low, rocks are brittle and tend to fracture when subjected to differential stress. Continued deformation grinds and pulverizes the mineral grains into smaller and smaller fragments. Chemically active fluids. Water is abundant in Earth's crust. In the upper crust, water occurs as groundwater. At depth, hot water is released into the surrounding rocks when a magma body cools and solidifies. In addition, many minerals, including clays, micas, and amphiboles, are hydrated, which means they contain water in their crystalline structures. Elevated temperatures and pressures cause these minerals to dehydrate, expelling hot, mineral-laden water. Hot, chemically active fluids enhance metamorphism by dissolving and transporting ions from one site in the crystal structure to another, thereby facilitating the process of recrystallization. In increasingly hotter environments, these fluids become correspondingly more reactive. In some metamorphic environments, hot fluids transport mineral matter over considerable distances. This occurs, for example, when hot, ion-rich fluids, called a hydrothermal solution, are expelled from a magma body as it cools and solidifies. If the rocks that surround the pluton differ markedly in chemical composition from the invading fluids, there may be an exchange of ions between these fluids and host rocks. In other words, these fluids bring in new atoms or take out atoms rather than simply reorganizing what is already present. When this occurs, the overall chemical composition of the surrounding rock changes, in a process called metasomatism. One example of metasomatism is the formation of the mineral wollastonite. From calcite, the primary ingredient in limestone. When a silica-rich hydrothermal solution invades limestone, calcite reacts with silica to generate wollastonite, and the gas carbon dioxide CO2 is driven off. The importance of parent rock. Most metamorphic rocks have the same overall chemical composition as the parent rocks from which they formed, except for the possible loss or acquisition of volatiles such as water H2O and carbon dioxide CO2. Therefore, when we try to establish from what parent material metamorphic rocks were derived, the most important clue comes from their overall chemical composition. Consider the large exposures of the metamorphic rock marble found high in the Alps of southern Europe. Because marble and the common sedimentary rock limestone have the same mineralogy, it seems reasonable to conclude that limestone is the parent rock of marble. Furthermore, because limestone usually forms in warm, shallow marine environments, we can surmise that considerable deformation must have occurred to convert limey deposits in a shallow sea into marble crags in the lofty Alps. The mineral makeup of the parent rock also largely determines the degree to which each metamorphic agent will cause change. For example, when magma forces its way into an existing body of rock, high temperatures and hot fluids may alter the host rock. If the host rock is composed of minerals that are comparatively non-reactive, such as quartz, any alterations that may occur will be confined to a narrow zone next to the igneous intrusion. However, when the host rock is limestone, which is highly reactive, the zone of metamorphism may extend far from the intrusion. Did you know? Some low-grade metamorphic rocks contain fossils. These fossils can provide useful clues for determining the original rock type and its depositional environment. In addition, fossils whose shapes have been distorted during metamorphism provide insight into the extent to which the rock has been deformed. Concept checks 8.2. 1. List 4 agents that drive metamorphism. 2. Why is heat considered the most important agent of metamorphism? 3. How is confining pressure different from differential stress? 4. What role do chemically active fluids play in metamorphism? 5. What characteristic of a metamorphic rock is determined primarily by its parent rock? 8.3 Metamorphic textures. Explain how foliated and non-foliated textures develop. The term texture is used to describe the size, shape, and arrangement of the mineral grains within a rock. Recall that texture is one characteristic by which igneous and sedimentary rocks are classified. Most igneous and many sedimentary rocks consist of mineral grains or crystals that have a random orientation and thus appear uniform when viewed from any direction. By contrast, metamorphic rocks that contain platy minerals and/or elongated minerals typically display some kind of preferred orientation, in which the mineral grains exhibit a parallel to subparallel alignment. Like a fistful of pencils, rocks containing elongated mineral grains that are oriented parallel to each other appear different when viewed from the side than when viewed head-on. A rock that exhibits a preferred orientation of its mineral constituents is said to possess foliation. Did you know? Glacial ice is a metamorphic rock that exhibits ductile flow, much like hot rocks buried deep within Earth's crust. Although we think of glacial ice as being cold, it is in fact hot relative to its melting temperature. Therefore, we should not be surprised that the ice within a glacier gradually flows downslope in response to the force of gravity. Foliation. The term foliation refers to any planar arrangement of mineral grains or crystals within a rock. Although foliation may occur in some sedimentary and even a few types of igneous rocks, it is a fundamental characteristic of metamorphosed rocks that have been strongly deformed, mainly by folding. In metamorphic environments, foliation is ultimately driven by compressional stress that shortens rock units, causing mineral grains in pre-existing rocks to develop parallel or nearly parallel alignments. Examples of foliation include the parallel alignment of platy minerals through rotation, recrystallization, and flattening of mineral grains or pebbles. Foliated textures include rock cleavage, in which rocks can be easily split into tabular slabs, and compositional banding, in which the separation of dark and light minerals generates a layered appearance. These diverse types of foliation can form in many different ways. Rotation of platy mineral grains. The rotation of existing mineral grains is the easiest of the foliation mechanisms to envision. Figure 8.7 illustrates the mechanics by which platy or elongated mineral grains are rotated. Note that the new alignment of the grains is roughly perpendicular to the direction of maximum stress. Although physical rotation of platy minerals contributes to the development of foliation in low-grade metamorphism, other mechanisms dominate in more extreme environments. Smart Figure 8.7 Mechanical rotation of platy mineral grains to produce foliation. Smart Figure 8.7 Full alternative text description. Recrystallization that produces new minerals. Watch animation, foliation. Recall that recrystallization is the creation of new mineral grains from pre-existing ones. When recrystallization occurs as rock is being subjected to differential stress, any elongated minerals and platy minerals that form tend to recrystallize perpendicular to the direction of maximum stress. Thus, the newly formed mineral grains exhibit a distinct layering, and the metamorphic rocks containing them exhibit foliation. Flattening spherically shaped grains. Mechanisms that flatten existing mineral grains are important in the metamorphism of rocks containing minerals such as quartz, calcite, and olivine. These minerals normally develop roughly spherical crystals and have a rather simple chemical composition. A change in grain shape can occur as distinct units of a mineral's crystalline structure slide relative to one another along discrete planes, thereby distorting the grain, as shown in Figure 8. 8. This type of gradual solid-state flow involves slippage that disrupts the crystalline structure as atoms shift positions by breaking existing chemical bonds and forming new ones. Mineral grains can be flattened by solid-state flow when units of a mineral's crystalline structure slide relative to each other. This mechanism involves breaking existing chemical bonds and forming new ones. Figure 8.8 Solid-state flow of mineral grains. Figure 8.8 Full alternative text description. The shape of a mineral may also be altered by a process in which individual atoms move from a location along the margin of the grain that is highly stressed to a less stressed position on the same grain. This mechanism, called pressure solution, is significantly aided by hot, ion-rich water. Mineral matter dissolves where grains are in contact with each other and is deposited in pore spaces. As a result, the mineral grains tend to become shortened in the direction of maximum stress and elongated in the direction of minimum stress. While both of these mechanisms flatten mineral grains, the mineralogy remains the same. Foliated textures. Various types of foliation exist, depending largely upon the grade of metamorphism and the mineralogy of the parent rock. We will look at 3: rock, or slaty, cleavage, schistosity, and gneissic texture, or banding. Rock, or slaty, cleavage. Rocks that split into thin slabs when hit with a hammer exhibit rock cleavage. Rock cleavage develops in various metamorphic rocks but is best displayed in slates that exhibit an excellent splitting property called slaty cleavage. Because it splits easily, slate is used for building materials such as roof and floor tiles as well as billiard table surfaces. Slaty cleavage is exhibited by the rock in the slate quarry. Because slate breaks into flat slabs, it has many uses. The inset photo shows the use of slate for the roof of a house in Switzerland. Figure 8.9 Excellent slaty cleavage. In low-grade metamorphic environments, slaty cleavage is known to develop where beds of shale are metamorphosed to form slate. The process begins when compressional stress begins to deform rock units, producing broad folds. Further deformation causes the clay minerals in shale, which initially aligned roughly parallel to the bedding surfaces, to begin recrystallizing into tiny flakes of chlorite and mica. However, these new platy mineral grains grow so they are aligned roughly perpendicular to the maximum differential stress, as shown in Figure 8.10b. When shale that is interbedded with sandstone is strongly folded and metamorphosed, the clay minerals begin to recrystallize into tiny flakes of chlorite and mica. These new platy minerals grow so they are aligned roughly perpendicular to the directed stress, which gives slate its foliation. Smart Figure 8.10 Development of rock cleavage. Smart Figure 8.10 Full alternative text description. Because slate typically forms during the low-grade metamorphism of shale, evidence of the original sedimentary bedding surfaces is often preserved. However, as Figure 8. 10c illustrates, the orientation of slate's cleavage usually develops at an angle to the sedimentary beds. Thus, unlike shale, which splits along bedding planes, slate often splits across bedding surfaces. Other metamorphic rocks, such as schists and gneisses, sometimes split along planar surfaces and thus also exhibit rock cleavage. Watch tutorial, Cleavage. Schistosity. At higher temperatures and pressures, the minute mica and chlorite flakes in slate begin to recrystallize into larger muscovite and biotite crystals. When these platy minerals are large enough to be discernible with the unaided eye, they exhibit planar or layered structures called schistosity. Rocks that have this type of foliation are termed schist. In addition to containing platy minerals, schist often contains deformed quartz and feldspar crystals that appear flattened or lens-shaped and are embedded among the mica grains. Gneissic texture, or banding. During high-grade metamorphism, ion migration can result in the segregation of minerals, as shown in Figure 8.11. Notice that the dark biotite and amphibole crystals and light silicate minerals have separated, giving the rock a banded appearance called gneissic texture, or gneissic banding. Metamorphic rocks with this texture are called gneiss. Although they are foliated, gneisses do not usually split as easily as slates and some schists. Figure 8.11 Development of gneissic banding. Gneissic banding develops through the migration of ions that cause felsic and mafic minerals to grow in separate layers. Figure 8.11 Full alternative text description. Other metamorphic textures. Metamorphic rocks that do not develop a layered or banded appearance as a result of metamorphism are referred to as non-foliated. Non-foliated metamorphic rocks typically form in metamorphic environments where deformation is minimal or when the parent rock is composed of minerals that develop equidimensional crystals rather than tabular-shaped crystals. For example, when a fine-grained limestone is metamorphosed, the small calcite grains in limestone recrystallize to form larger uniform-shaped crystals. The resulting metamorphic rock, marble, consists of intergrown calcite crystals that lack banding and are similar in appearance to the crystals in coarse-grained igneous rocks. Another common non-foliated metamorphic rock, called hornfels, is generated when clay-rich rocks like shale and mudstone are intruded by a hot magma body. In this environment, where differential stress tends to be absent, the rocks are baked to produce a tough rock that lacks alignment of its platy mineral grains. Metamorphic rocks may also contain some unusually large grains, called porphyroblasts, that are surrounded by a fine-grained matrix of other minerals. Porphyroblastic textures develop in a wide range of rock types and metamorphic environments when minerals in the parent rock recrystallize to form new minerals. During recrystallization, certain metamorphic minerals, such as garnet, tend to develop a small number of very large crystals. By contrast, minerals such as muscovite and biotite typically form a large number of smaller grains. As a result, metamorphic rocks that contain large crystals of, for example, garnet embedded in a finer-grained matrix of biotite and muscovite, are relatively common. The dark red garnet crystals are embedded in a matrix of fine-grained micas. Concept checks 8.3. 1. Define foliation. 2. Briefly describe 3 ways in which the mineral grains in a rock develop a preferred orientation. 3. Distinguish among slaty cleavage, schistosity, and gneissic textures. 4. What is meant by non-foliated texture? Name one rock that exhibits this texture. Figure 8.12 Garnet, mica schist. 8.4 Common metamorphic rocks. List and describe the most common metamorphic rocks. Most metamorphic rocks that we observe at Earth's surface were derived from the 3 most common sedimentary rocks: shale, limestone, and quartz sandstone. Shale is the most likely parent of most slate, phyllite, schist, and gneiss. This sequence of metamorphic rocks reflects an increase in grain size, a change in rock texture, and a change in mineralogy. Limestone, which is composed of the mineral calcite, is the parent rock of marble, while quartz sandstone is the parent of quartzite. Because calcite and quartz are simple chemical compounds compared to clay minerals, their mineralogy does not change during metamorphism. Calcite usually remains calcite, and quartz remains quartz. Rather, these minerals recrystallize to produce larger fused grains that are the main constituents of marble and quartzite, respectively. The major characteristics of the most common metamorphic rocks are summarized in Figure 8. 13. Notice that metamorphic rocks can be broadly classified by the type of foliation exhibited and, to a lesser extent, the chemical composition of the parent rock. It is worth noting that certain rock names are also used to describe rock texture. Figure 8.13 Classification of common metamorphic rocks. Figure 8.13 Full alternative text description. Foliated metamorphic rocks. Slate. A very fine-grained foliated rock composed mainly of minute chlorite and mica flakes is termed slate. Slate may also contain tiny quartz and feldspar crystals. Thus, slate generally appears dull and closely resembles shale. A noteworthy characteristic of slate is its excellent rock cleavage, or tendency to break into flat slabs. Slate is most often generated by the low-grade metamorphism of shale, mudstone, or siltstone. Less frequently it is produced when volcanic ash is metamorphosed. Slate's color depends on its mineral constituents, black. Slate contains organic material. Red slate gets its color from iron oxide, and green slate usually contains a lot of the mineral chlorite. Phyllite. Phyllite represents a degree of metamorphism between slate and schist. Its constituent platy minerals are larger than those in slate but not large enough to be readily identifiable with the unaided eye. Although similar to slate in appearance, phyllite can be easily distinguished from slate by its glossy sheen and wavy surface. Phyllite exhibits rock cleavage and is composed mainly of very fine crystals of muscovite, chlorite, or both. Schist. Medium to coarse-grained metamorphic rocks in which platy minerals are dominant are called schists. These flat components commonly include muscovite and biotite with parallel alignments that give the rock its foliated texture. In addition, schists contain smaller amounts of other minerals, often quartz and feldspar. Some schists are composed mostly of dark minerals. As with slate, the parent rock of most schists is shale that has undergone medium to high-grade metamorphism during a major mountain-building episode. This sample of schist, composed mostly of muscovite and biotite, exhibits foliation. Figure 8.14 Mica schist. As you learned in the previous section, the term schist describes the texture of rocks, and as such it is used to name rocks that have a wide variety of chemical compositions. To indicate composition, mineral names are added. For example, schists composed primarily of muscovite and biotite are called mica schist. Mica schists often contain accessory minerals, some of which are unique to metamorphic rocks. Some common accessory minerals that occur as porphyroblasts include garnet, staurolite, and andalusite, in which case the rock is called garnet mica schist, staurolite mica schist, or andalusite mica schist. In addition, schists may be composed largely of the minerals chlorite or talc, in which case they are called chlorite schist and talc schist, respectively. Both chlorite and talc schists can form when rocks having basaltic compositions undergo metamorphism. Gneiss. Gneiss is the term applied to medium to coarse-grained banded metamorphic rocks in which granular and elongated minerals predominate. The most common minerals in gneiss are quartz, potassium feldspar, and plagioclase feldspar. Most gneisses also contain lesser amounts of biotite, muscovite, and amphibole. Some gneisses split along the layers of platy minerals, but most break in an irregular fashion. Recall that during high-grade metamorphism, the light and dark components separate, giving gneisses their characteristic banded or layered appearance. Thus, most gneisses consist of alternating bands of white or reddish feldspar-rich zones and layers of dark ferromagnesian minerals. These banded gneisses often exhibit evidence of deformation, including folds and sometimes faults. Gneisses having a felsic composition may be derived from granite or its fine-grained equivalent, rhyolite. However, most gneisses are generated through high-grade metamorphism of shale. Therefore, gneiss represents the highest-grade metamorphic rock in the sequence of shale, slate, phyllite, schist, and gneiss. Like schists, gneisses may also include large crystals of accessory minerals such as garnet. Gneisses made up primarily of dark minerals also occur. For example, an amphibole-rich rock that exhibits a gneissic texture is called amphibolite. Figure 8.15 Banded gneiss found in the Adirondacks, New York. Did you know? Rocks of the Acasta Gneiss Complex, exposed just east of Great Slave Lake in the Northwest Territories of Canada, have yielded radiometric dates of up to 4.03 billion years. These are currently the oldest known rocks in the world. Non-foliated metamorphic rocks. Marble. The metamorphism of limestone or dolostone produces the crystalline metamorphic rock called marble. Pure marble is white and composed essentially of the mineral calcite. Because of its relative softness, marble is easy to cut and shape. White marble is particularly prized as a stone from which monuments and statues are carved, such as the Lincoln Memorial in Washington, D.C., and the Taj Mahal in India. Unfortunately, when exposed to acid rain, marble's composition makes it susceptible to chemical weathering. The exterior of India's Taj Mahal is constructed primarily of the metamorphic rock marble. The parent rocks of most marbles contain impurities that color the stone. Thus, marble can be pink, gray, green, or even black and may contain a variety of accessory minerals, such as chlorite, mica, garnet, and wollastonite. When marble forms from limestone interbedded with shales, it appears banded and exhibits visible foliation. When deformed, these banded marbles may develop highly contorted mica-rich folds that enhance the rock's artistic appearance. These decorative marbles have been used as building stones since prehistoric times. Quartzite. Figure 8.16 Marble is a widely used building stone. Quartzite is a very hard metamorphic rock formed from quartz sandstone. Under moderate to high-grade metamorphism, the quartz grains in sandstone fuse together. Recrystallization is often so complete that, when broken, quartzite splits across the original quartz grains rather than along their boundaries. In some instances, sedimentary features such as crossbedding are preserved and give the rock a banded appearance. Pure quartzite is white, but iron oxide may produce reddish or pinkish stains, while dark mineral grains may impart shades of green or gray. Quartzite is a non-foliated metamorphic rock formed from quartz sandstone. The close-up images compare the loosely bound grains in a quartz sandstone to the interlocking quartz grains typical of quartzite. Figure 8.17 Quartzite. Hornfels. A fine-grained non-foliated metamorphic rock, hornfels is unlike marble and quartzite in that it has a variable mineral composition. The parent rock of most hornfels is shale or another clay-rich rock that has been baked by a hot intruding magma body. Hornfels tends to be gray to black in color and quite hard, and it may display conchoidal fracture. Concept checks 8.4. 1. Although slate and phyllite resemble each other, how can they be differentiated? 2. For the rock mica schist, what does mica indicate, and what does schist indicate? 3. Briefly describe the appearance of the metamorphic rock gneiss and explain how it forms. 4. Describe slate, phyllite, schist, and gneiss in terms of texture and grain size. 5. Compare and contrast marble and quartzite. 8.5 Metamorphic environments. Write a description for each of these metamorphic environments, contact metamorphism, hydrothermal metamorphism, subduction zone metamorphism, and regional metamorphism. There are many different environments in which metamorphism occurs. Most of these environments occur in the vicinity of plate margins, and several are associated with igneous activity. We will consider the following basic metamorphic environments: contact or thermal metamorphism, hydrothermal metamorphism, burial and subduction zone metamorphism, and regional metamorphism, as well as a few types of metamorphism that generate relatively small quantities of metamorphic rock. As Figure 8.18 illustrates, each type of metamorphism occurs over a range of temperatures and pressures. On this graph, temperature, which increases from surface conditions to about 1000 C, is displayed along the top, and pressure is shown along the vertical axis. Notice that hydrothermal metamorphism occurs in relatively low temperature and low pressure environments, whereas burial and subduction metamorphism occur under relatively low temperature and high pressure conditions. Although not shown on this graph, regional and subduction metamorphism involve differential stress, whereas hydrothermal and contact metamorphism do not. This graph illustrates the temperatures and pressures typically associated with the major types of metamorphic environments. Figure 8.18 Metamorphic environments. Figure 8.18 Full alternative text description. Contact, or thermal, metamorphism. Contact metamorphism, or thermal metamorphism, occurs in Earth's upper crust, when rocks immediately surrounding a molten igneous body are baked. Because contact metamorphism does not involve differential stress, the resulting metamorphic rocks are not foliated. Contact metamorphism alters rocks in a discrete zone adjacent to the heat source, called an aureole. The emplacement of small intrusions such as dikes and sills typically form aureoles only a few centimeters thick. By contrast, large molten bodies that eventually cool to form batholiths can produce aureoles that extend outward for several kilometers. These large aureoles often consist of distinct zones of metamorphism. Close to the magma body, high-temperature minerals such as garnet may form, whereas farther away, low-grade metamorphism produces minerals such as chlorite. Smart Figure 8.19 Contact metamorphism. Contact metamorphism produces a zone of alteration called an aureole around an intrusive igneous body. In the photo, the dark layer is a type of metamorphic aureole called a roof pendant, which consists of metamorphosed host rocks that are in contact with the upper part of the light-colored igneous pluton. The term roof pendant implies that the rock was once the roof of a magma chamber. The photo shows the Sierra Nevada, near Bishop, California. Figure 8.19 Full alternative text description. Watch tutorial, Contact metamorphism. Did you know? One of America's worst civil engineering disasters occurred in 1928 when the St. Francis Dam in Southern California failed. Huge torrents of water washed down San Francisco Canyon, destroying 900 buildings and taking nearly 500 lives. The eastern part of the dam was built on highly foliated mica schist that was prone to slippage, as evidenced by an earlier landslide in that area. The immense water pressure at the base of the dam and the weak schist to which it was anchored are thought to have contributed to the failure. Depending mainly on the composition of the parent rock, a variety of metamorphic rocks can form in the same setting. For example, during contact metamorphism of mudstones and shales, the clay minerals are baked, much as clay is baked in a kiln to make pottery. The result is a very hard, fine-grained metamorphic rock called hornfels. Hornfels can also form from a variety of other materials, including volcanic ash and basaltic rocks. Other metamorphic rocks that are produced by contact metamorphism are marble and quartzite. Recall that limestone is the parent of marble and that the metamorphism of quartz sandstone produces quartzite. Contact metamorphism of shale yields hornfels, while contact metamorphism of quartz sandstone and limestone produces quartzite and marble, respectively. Figure 8.20 Full alternative text description. Hydrothermal metamorphism. When hot, ion-rich water circulates through pore spaces or fractures in rock, a chemical alteration called hydrothermal metamorphism may occur. Recall that hot mineral-laden fluids called hydrothermal solutions contribute to metamorphism by enhancing the recrystallization of existing minerals. In addition, hot ion-rich fluids facilitate the movement of mineral matter into and out of rock bodies, thereby changing their overall chemical composition. Figure 8.20 Rocks produced by contact metamorphism. Pegmatites and hydrothermal mineral deposits form adjacent to an igneous intrusion. Figure 8.21 Full alternative text description. The water for hydrothermal metamorphism can be groundwater that has percolated down from the surface, where it is heated and circulates upward. This type of metamorphism tends to occur at low pressures and relatively low to moderate temperatures. Figure 8.21 Hydrothermal metamorphism associated with an intrusive igneous body. Water that drives hydrothermal metamorphism may also arise from igneous activity. As large magma bodies cool and solidify, ion-rich water is released into the surrounding host rocks. When the host rock is porous or highly fractured, mineral matter contained in these fluids may precipitate to form important deposits of copper, silver, and gold. These ion-rich fluids can also generate pegmatites, very coarse-grained granitic igneous rocks. As scientific understanding of plate tectonics developed, it became clear that the most widespread occurrence of hydrothermal metamorphism is along the axis of the mid-ocean ridge system. As plates move apart, upwelling magma from the mantle generates new seafloor. Seawater percolating through the young, hot oceanic crust is heated and chemically reacts with the newly formed basaltic rocks. The result is the conversion of mafic rocks of the oceanic crust and uppermost mantle into the hydrated rocks serpentinite and soapstone. Figure 8.22 Hydrothermal metamorphism along a mid-ocean ridge. Figure 8.22 Full alternative text description. These metamorphic rocks are produced by hydrothermal alteration of mafic rocks along the mid-ocean ridge system. Figure 8.23 Serpentinite and soapstone. Hydrothermal solutions circulating through the seafloor also remove large amounts of metals, such as iron, cobalt, nickel, silver, gold, and copper, from the newly formed crust. These hot, metal-rich fluids eventually rise along fractures and gush from the seafloor at temperatures of about 350 C, generating particle-filled clouds called black smokers. Upon mixing with the cold seawater, sulfides and carbonate minerals containing these heavy metals precipitate to form metallic deposits. Geologists credit this process with the formation of the copper ores mined today on the Mediterranean island of Cyprus. Burial and subduction zone metamorphism. Burial metamorphism tends to occur where massive amounts of sedimentary or volcanic material accumulate in a subsiding basin, such as the Gulf of Mexico. Here, low-grade metamorphic conditions may be reached within the deepest layers. Confining pressure and heat drive the recrystallization of the constituent minerals, changing the texture and or mineralogy of the rock without appreciable deformation. Rocks and sediments can also be carried to great depths along convergent boundaries where oceanic lithosphere is being subducted. In this setting, cold, dense oceanic crust and sediments, which are poor conductors of heat, are subducting rapidly enough that pressure increases faster than temperature. This phenomenon, called subduction zone metamorphism, differs from burial metamorphism in that differential stress, rather than confining pressure, plays a major role in deforming rock as it is being metamorphosed. Regional metamorphism. Regional metamorphism is a common, widespread type of metamorphism typically associated with mountain building, where large segments of Earth's crust are intensely deformed by the collision of two continental crust blocks. Recall that denser oceanic crust subducts under more buoyant continental crust, but that two land masses will instead collide and deform. Sediments and crustal rocks that form the margins of the colliding continents are folded and faulted and, as a result, shorten and thicken like a rumpled carpet. Continental collisions may also cause crystalline basement rocks lying under sedimentary layers, as well as slices of oceanic crust that once floored the intervening ocean basin, to be uplifted and deformed. Figure 8.24 Regional Metamorphism. Regional metamorphism is often associated with a continental collision where rocks are squeezed between two converging crustal blocks, resulting in mountain building. Figure 8.24 Full alternative text description. The general thickening of the crust that occurs during mountain building results in buoyant lifting, in which deformed rocks are elevated high above sea level. Crustal thickening also results in the deep burial of large quantities of rock as one crustal block is thrust beneath another. Deep in the roots of mountains, elevated temperatures caused by deep burial are responsible for the most intense metamorphic activity within a mountain belt. In some settings, deeply buried rocks become heated beyond their melting points, producing magma. When these magma bodies grow large enough to buoyantly rise, they intrude the overlying metamorphic and sedimentary rocks. Consequently, the cores of many mountain belts consist of folded and faulted metamorphic rocks, often intertwined with igneous bodies. Over time, these deformed rock masses are uplifted, and erosion removes the overlying material to expose the igneous and metamorphic core of the mountain range. Regional metamorphism produces some of the most common metamorphic rocks. In these settings, shale is metamorphosed to produce the sequence of slate, phyllite, schist, and gneiss. In addition, quartz sandstone and limestone are metamorphosed into quartzite and marble. Other metamorphic environments. Other, less common types of metamorphism generate relatively small amounts of metamorphic rock that tends to be geographically localized. Did you know? Most pigment that gives paint its color and its ability to hide previous coats comes from various natural earth materials. For example, umber, which produces a rich chestnut brown color, is mined on the island of Cyprus. This material was formed on an ancient seafloor by the hydrothermal alteration of iron and manganese-rich basaltic lavas. Metamorphism along fault zones. Near Earth's surface, rock behaves like a brittle solid. Consequently, movement along a fault zone fractures and pulverizes rock. The result is a loosely coherent rock called fault breccia, composed of broken and crushed rock fragments. Displacements along California's San Andreas Fault have created a zone of fault breccia and related rock types more than 1,000 kilometers long and up to 3 kilometers wide. Smart Figure 8.25 Metamorphism along a fault zone. Smart Figure 8.25 Full alternative text description. Much of the deformation associated with fault zones occurs at great depth and thus at high temperatures. In this environment, pre-existing minerals deform by ductile flow. As large slabs of rock move in opposite directions, the minerals in the fault zone between them tend to form elongated grains that give the rock a foliated and/or lineated appearance. Rocks formed in these zones of intense ductile deformation are termed mylonites. Impact metamorphism. Watch tutorial, Mylonite and fault breccia. Impact, or shock, metamorphism occurs when meteorites strike Earth's surface at high speeds. Upon impact, the energy of the once rapidly moving meteorite is transformed into heat energy and shock waves that pass through the surrounding rocks. The result is pulverized, shattered, and sometimes melted rock. Did you know? Although they are rare, metamorphic rocks that contain microscopic diamonds have been discovered at Earth's surface. The existence of diamonds in metamorphic rocks indicates that these rocks formed at very high pressures found at depths of at least 60 miles. How these metamorphic rocks were buried to these great depths and later returned to the surface is still a mystery. The products of these impacts, called impactals, include mixtures of fused fragmented rock plus glass-rich ejecta that resemble volcanic bombs. In some cases, a very dense form of quartz and minute diamonds are found. The existence of these high-pressure minerals provides convincing evidence that pressures and temperatures involved in impact metamorphism can be as great as those found in the upper mantle. Concept checks 8.5. 1. In which type of metamorphism does compressional stress play a major role? 2. Name 3 rocks that are produced by contact metamorphism. 3. What is an aureole? 4. What is the agent of hydrothermal metamorphism? 5. Which type of plate boundary is typically associated with regional metamorphism? 6. List the common metamorphic rocks generated by regional metamorphism. 8.6 Metamorphic zones. Explain how index minerals are used to establish the metamorphic grade of a rock body. In areas affected by metamorphism, geologists can observe the usually systematic variations in the mineralogy and texture of the altered rocks. These differences are clearly related to variations in the degree of metamorphism that takes place in each metamorphic zone. Textural variations. Across areas where regional metamorphism has occurred, rock textures vary based on the intensity of metamorphism. If we begin with a clay-rich sedimentary rock such as shale or mudstone, a gradual increase in metamorphic intensity from low grade to high grade is accompanied by a general coarsening of the grain size. Figure 8. 26 illustrates that as metamorphic intensity increases, shale changes to a fine-grained slate, which then forms phyllite, which, through continued recrystallization, generates a medium-grained schist. Under more intense conditions, a gneissic texture that exhibits layers of dark and light minerals may develop. This systematic transition in metamorphic textures can be observed as we approach the Appalachian Mountains from the west. Beds of shale, which once extended over large areas of the eastern United States, still occur as nearly flat-lying strata in Ohio. However, in the broadly folded Appalachians of central Pennsylvania, the rocks that once formed flat-lying beds are folded and display a preferred orientation of platy mineral grains, as exhibited by well-developed slaty cleavage. As we move further east, toward the intensely deformed crystalline Appalachians, we find large exposures of schists. Some of the most intense zones of metamorphism are found in Vermont and New Hampshire, where gneissic rocks are exposed at the surface. Idealized illustration of textural variations produced by regional metamorphism, progressing from low-grade metamorphism to high-grade metamorphism. Smart Figure 8.26 Textural variations caused by regional metamorphism. Smart Figure 8.26 Full alternative text description. Highly generalized map that shows areas of low to high-grade metamorphism in New England. Watch tutorial, Progressive Regional Metamorphism. Figure 8.27 Zones of metamorphic intensities in New England. Figure 8.27 Full alternative text description. Index minerals and metamorphic grade. In addition to textural changes, we encounter corresponding changes in mineralogy as we shift from areas of low-grade metamorphism to areas of high-grade metamorphism. An idealized transition in mineralogy that results from the regional metamorphism of shale is shown in Figure 8.28. The first new mineral to form as shale changes to slate is chlorite. At higher temperatures, flakes of muscovite and biotite begin to dominate. Under more extreme conditions, metamorphic rocks may contain garnet and or staurolite crystals. At temperatures approaching the melting point of rock, sillimanite forms. Sillimanite is a high-temperature metamorphic mineral used to make porcelains used in extreme environments, such as for spark plugs. This is a typical transition of various index minerals associated with the progression from low-grade to high-grade metamorphism of the rock shale. Figure 8.28 Full alternative text description. These garnet porphyroblasts are found in a gneiss in the Adirondacks, New York. Figure 8.28 Metamorphic Zones and Index Minerals. Smart Figure 8.29 Garnet, an index mineral, provides evidence of medium to high-grade metamorphism. Through the study of metamorphic rocks in their natural settings and through experimental studies, researchers have learned that certain minerals, such as those listed in Figure 8.28, are good indicators of the metamorphic environment in which they formed. Using these index minerals, geologists distinguish among different zones of regional metamorphism. For example, the mineral chlorite begins to form when temperatures are relatively low, less than 200 C. Thus, rocks containing chlorite are categorized as low-grade. By contrast, the mineral sillimanite forms only in extreme environments where temperatures exceed 600 C, and rocks containing it are considered high-grade. By mapping the occurrences of index minerals, geologists can identify zones of varying metamorphic grades. Watch Mobile Field Trip: Metamorphic Rocks of the Adirondack Mountains. Migmatites. In the most extreme environments, even the highest-grade metamorphic rocks undergo change. For example, gneissic rocks may be heated sufficiently to trigger melting. However, minerals melt at different temperatures. The light-colored silicates, usually quartz and potassium feldspar, have the lowest melting temperatures and begin to melt first, while the mafic silicates, such as amphibole and biotite, remain solid. When the partially melted rock cools, the light bands will be composed of igneous or igneous-appearing components, while the dark bands will consist of unmelted metamorphic material. Rocks of this type are called migmatites. The light color bands in migmatites often form intricate folds and may contain tabular inclusions of the dark components. Migmatites serve to illustrate the fact that some rocks are considered transitional and do not fit neatly into any of the three basic rock groups. Under high-grade metamorphism, light-colored minerals in a gneiss may begin to melt, while the dark-colored minerals remain solid. If this melt solidifies in place, the rock, called a migmatite, will contain light-colored igneous rock intermixed with metamorphic rock composed of dark-colored minerals. Figure 8.30 Migmatite. Concept checks 8.6. 1. Describe the different grades of metamorphism that might be encountered moving west to east from Ohio to the crystalline core of the Appalachians. 2. How do geologists use index minerals? 3. Explain why migmatites are difficult to place into any one of the three basic rock groups. Concepts in review: metamorphism and metamorphic rocks. 8.1 What is metamorphism? Compare and contrast the environments that produce metamorphic, sedimentary, and igneous rocks. Key terms: parent rock metamorphism, mineralogy, metamorphic grade. Rocks subjected to elevated temperatures and pressures can react and change form to produce metamorphic rocks. Every metamorphic rock has a parent rock, the rock it was prior to metamorphism. New minerals form when minerals and parent rocks undergo metamorphosis. Metamorphic reactions tend to produce larger crystals and may generate layers or bands of minerals aligned in a common direction. Metamorphic grade describes the intensity of metamorphosis. Low-grade metamorphic rocks strongly resemble their parent rock. High-grade metamorphism destroys textures of parent rocks and features such as fossils. Metamorphism takes place in the solid state and in most cases does not involve any melting. Compare the processes that produce metamorphic rocks to those that produce igneous or sedimentary rocks. 8.2 What drives metamorphism? List and distinguish among the four agents that drive metamorphism. Key terms: recrystallization, geothermal gradient, confining pressure, differential stress, compressional stress. Heat, pressure, differential stress, and chemically active fluids are four agents that drive metamorphic reactions. Any one alone may trigger metamorphism, or all four may exert influence simultaneously. The burial of rock or the intrusion of a nearby magma body will raise the temperature of a rock. Heat provides energy that drives chemical reactions and results in the recrystallization of the existing minerals. Different minerals have different levels of susceptibility to recrystallization. Some crystals just grow larger, while others react to form new minerals. Quartz is stable across a wide range of temperatures, whereas clay minerals are stable only at low temperatures. Confining pressure, which results from burial, is analogous to water pressure in that force is exerted equally in all directions. An increase in confining pressure causes rocks and minerals to compact into more dense configurations. Differential stress results from tectonic forces, where the pressure is greater in some directions than in others. Rocks subjected to differential stress deep in Earth's crust tend to respond in a ductile manner, shortening in the direction of greatest stress and elongating in the direction of least stress, producing flattened or stretched grains. If the same differential stress is applied to a rock in the shallow crust, the rock may deform in a brittle fashion instead, breaking into smaller pieces. Water is an important chemically active fluid in Earth's crust. Hot water can facilitate numerous chemical reactions and may transport dissolved mineral matter great distances to new locations. This may alter the composition of the metamorphosing rock by introducing or removing certain elements. Draw a sketch illustrating the difference between confining pressure and differential stress. 8.3 Metamorphic textures. Explain how foliated and non-foliated textures develop. Key terms: texture, foliation, rock cleavage, slaty cleavage, schistosity. Gneissic texture, non-foliated. Porphyroblastic texture. Texture can reveal the orientation of stresses that helped form a metamorphic rock. A common metamorphic texture is foliation, the planar arrangement of mineral grains. Foliation forms perpendicular to the direction of maximum differential stress, through a combination of processes: rotation of mineral grains, recrystallization and growth of new mineral grains, and flattening of grains by solid-state flow or pressure solution. Several arrangements of mineral grains are classified as varieties of foliation, including slaty cleavage, schistosity, and gneissic banding. Metamorphic rocks that do not exhibit foliation are described as non-foliated. For example, marble, which is a non-foliated metamorphic rock, forms when small calcite grains in apparent limestone grow into a mass of large uniformly shaped crystals. Porphyroblasts are unusually large crystals of certain minerals, such as garnet, that form in an otherwise finer-grained metamorphic rock. They represent the tendency of some minerals to form a small number of large crystals during recrystallization, while other minerals form a large number of smaller crystals. Examine the accompanying photograph. Is this rock foliated or non-foliated? Which pair of arrows shows the direction of maximum stress? Figure 8.8-1 Full alternative text description. 8.4 Common metamorphic rocks. List and describe the most common metamorphic rocks. Key terms: slate, phyllite, schist, gneiss, marble. Quartzite, hornfels. Common foliated metamorphic rocks include slate, phyllite, schist, and gneiss. Common non-foliated metamorphic rocks include quartzite, marble, and hornfels, which form from quartz sandstone, limestone, and shale, respectively. If you were on a class field trip and found an outcrop of non-foliated light-colored rock, how would you determine whether it is quartzite or marble? How would you distinguish quartzite from quartz sandstone? 8.5 Metamorphic environments. Write a description for each of these metamorphic environments: contact metamorphism, hydrothermal metamorphism, subduction zone metamorphism, and regional metamorphism. Key terms: contact metamorphism, boreal. Hydrothermal metamorphism, burial metamorphism. Subduction zone metamorphism, regional metamorphism, impact metamorphism. Metamorphism can be triggered by diverse geologic situations. Convergent and divergent plate boundaries are both sites of metamorphism, as are deep stacks of sediments on passive margins. Contact metamorphism occurs in Earth's upper crust when heat from a molten igneous body bakes the surrounding rocks in a zone called the aureole. Differential stress is typically absent, so the rocks are not foliated. Hydrothermal metamorphism occurs when hot, ion-rich water circulates through pore spaces or fractures in rock. These fluids enhance recrystallization and can also import or export elements, changing the rock's chemical composition. Hydrothermal metamorphism produces economically important deposits of metal ore. Burial metamorphism occurs when rocks are buried beneath kilometers of overlying rock. Under confining pressure, elevated temperatures cause metamorphic reactions. Subduction zone metamorphism is similar, but with the added influence of differential stress. Continental collisions produce regional metamorphism. Rocks at these sites of crustal thickening are subjected to both high temperatures and differential pressure. The resulting belts of metamorphic rock mark zones where continental blocks collided to produce mountains. Long after the mountains have worn away, the collision site is marked by a deformed zone of regional metamorphic rocks that may include slate, schist, marble, and gneiss. Other distinctive varieties of metamorphism are associated with faults and meteorite impacts. 8.6 Metamorphic zones. Explain how index minerals are used to establish the metamorphic grade of a rock body. Key terms. Index mineral migmatite. The amount of change in metamorphic rocks increases as the rocks are exposed to higher temperatures and pressures. Metamorphic rocks reveal the degree of metamorphism through their textures and the minerals they contain. Grain size increases with higher levels of metamorphism. Under progressively higher temperatures and pressures, shale may transform first to slate, then to phyllite, to schist, and to gneiss. Certain minerals can act as indicators of the environment that a metamorphic rock experienced. Chlorite is a mineral associated with low-grade metamorphism, whereas garnet and staurolite are index minerals for intermediate metamorphic grades. Sillimanite indicates a high metamorphic grade. In extreme metamorphic environments, the minerals with the lowest melting points may melt while the mafic minerals with higher melting points remain solid. The resulting rocks, called migmatites, consist of light and dark bands that may be intricately folded. When exposed to metamorphic conditions over sufficient time, shale becomes schist. This sample of schist contains porphyroblasts of sillimanite. Do these porphyroblasts indicate low-, intermediate-, or high-grade metamorphism? Give it some thought. 1. Each of the following statements describes one or more characteristics of a particular metamorphic rock. For each statement, identify the metamorphic rock or rocks being described. A. Calcite-rich and non-foliated. B. Loosely coherent and composed of broken fragments that formed along a fault zone. C. Represents a grade of metamorphism between slate and schist. D. Composed of tiny chlorite and mica grains and displaying excellent rock cleavage. E. Foliated and composed predominantly of platy materials. F. Composed of alternating bands of light and dark silicate minerals. G. Hard and non-foliated, often produced by contact metamorphism. 2. Examine the accompanying close-up images of a conglomerate and a metaconglomerate. A. Describe how the conglomerate is different from the metaconglomerate. B. Does this metaconglomerate appear to have been exposed to significant differential stress? Explain. 3. Describe the textural changes that occur as shale goes from low to high metamorphic grade, forming, successively, slate, schist, and gneiss. 4. Examine the accompanying photos that show the geology of the Grand Canyon. Notice that most of the canyon consists of layers of sedimentary rocks, but if you were to hike into the inner gorge, you would encounter the Vishnu schist, a metamorphic rock. A. What process might have been responsible for the formation of the Vishnu schist? B. What does the Vishnu schist tell you about the history of the Grand Canyon prior to the formation of the canyon itself? C. Why is the Vishnu schist visible at Earth's surface? D. Is it likely that rocks similar to the Vishnu schist exist elsewhere but are not exposed at Earth's surface? Explain. 5. One of the rock outcrops in the accompanying photos consists mainly of metamorphic rock. Which do you think it is? Explain why you ruled out the other rock bodies. 6. Refer to the accompanying diagram and match each labeled area with the appropriate environment listed below. A. Contact metamorphism. B. Subduction metamorphism. C. Regional metamorphism. D. Burial metamorphism. E. Hydrothermal metamorphism. Figure 8.8 to 1 full alternative text description. 7. Based on the information provided in Figure 8.27, complete the following. A. Describe how the metamorphic grade changes from west to east across New England along line A, B. B. How might these metamorphic rocks have formed? C. Are these zones of metamorphism consistent with the current tectonic setting of New England? Explain. 8. Examine the accompanying close-up images of 6 different rocks labeled A, F. Classify them as igneous, sedimentary, or metamorphic, based on texture. Figure 8.8 to 1 full alternative text description. 9. The accompanying image shows a metamorphic rock located in Purgatory Chasm in Newport, Rhode Island, that is made of elongated cobbles composed mainly of quartz. A. What name would you give to this metamorphic rock? B. Which set of arrows best represents the direction of maximum differential stress? C. Is this type of deformation best described as ductile or brittle? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 9: Earthquakes and Earth's Interior. Tsunami striking the coast of Minamisoma, Japan on March 11, 2011. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 9.1 Sketch and describe the mechanism that generates most earthquakes. 9.2 Compare and contrast the types of seismic waves and describe the principle of the seismograph. 9.3 Explain how seismographs are used to locate the epicenter of an earthquake. 9.4 Distinguish between intensity scales and magnitude scales. 9.5 List and describe the major destructive forces that earthquake vibrations can trigger. 9.6 Locate Earth's major earthquake belts on a world map. 9.7 Compare and contrast the goals of short-range earthquake predictions and long-range forecasts. 9.8 Explain how Earth acquired its layered structure and name and describe each of its major layers. On April 25, 2000